Hi, welcome back to MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 22 in the series, Introduction to Functions. So in previous videos, we've talked about how with equations that have two variables in them, if we solve for one of the variables in terms of the other, we could sort of think about this in terms of output and input. We think about y here as being the output, something that we get when we plug in numbers for x. So x would be our input. If we replace x with a given number, then we will get a output, which is a given number y. For example, if I plug in 2, I would get 3 times 2 is 6, plus 1 is 7. So we think about this in terms of an output, an input, and some stuff that we have to do to that input, some rules, some instructions that are going to tell me what to do with x. In this case, times it by 3 and add 1 to it. Now, functions are an abstraction or a generalization about this idea. And we like to abstract things in mathematics because when we get things to be more general, there's sometimes larger classes of problems that we can tackle with them. But the main idea of a function is that there's some input that goes in, like our x before. There's some rules and operations, like our times 3 plus 1. And then there's some output that pops out. This is the much-drawn factory model of the function. But functions themselves are even a special case of a more general object, which we should talk about first. Functions are special in that they only give you this one single output back. They don't spit out two things when you put in a single x, they spit out one thing. And when we plug in the same value of x, there's not some randomness here that gives me different values at different times. It only gives me one value for any one input. So that kind of begs the question, what is the thing which actually does multiple outputs? These are called relations. We won't talk about that random business I mentioned before, although those do exist. Those are called stochastic functions. That's a topic for a different course. But we will talk about relations. So I want you to actually begin with the definition of a relation. Copy this for your critical notes. This is what a relation is. Let A and B be sets. Any sets. Could be sets of numbers. For most of our class, we'll be dealing with sets of numbers, but they could just be sets of objects. A relation is an assignment that takes every single element in the set A and assigns it a corresponding element in B. And we write those as an ordered pair, A comma B. I know, more notation abuse. The coordinate pair and the interval, and now relations too. Yes, yeah, but the coordinate pair and this relation are going to turn out to have a lot in common. So maybe this isn't such bad notational abuse. But you should know that this is a new use of the parentheses. It's saying a element A assigned to an element B. Now, that's the definition, but what does that really mean? The way you should think about a relation is that it's some kind of rule that makes pairs. It takes a number or an element from an input set, and it pairs it up with a number or an element from an output set. Let's start with a simple example. Here's a set of three numbers, 1, 2, and 3. Here's a set of three numbers, 4, 5, and 6. Now, the rule to make a relation on this is that we have to make up a element of B for every single element of A. Okay, so now let's make a particular relation on these two sets. I assign 1 to 4, and haha, I also assign 1 to 5. Now, nothing says I couldn't do this. It only said that I had to use everything in A. It didn't say that I couldn't use something twice. We'll find that's actually what makes this thing different than a function. But for right now, let's just go with it. And then let's say that this thing also assigns 2 to 4, and it assigns 3 to 5. Notice I never hit 6. That's okay. Nothing ever said I had to hit everything in B. That's actually a special kind of relation. We'll talk about that more later. One of the ways we can represent this relation is with a map diagram. So here I have drawn a little egg to represent A, and I put A's elements inside. Then I drew some arrows to represent the assignments. 1 went to 4, 1 went to 5, 2 went to 4, and 3 went to 5. So this green part here is my relation. And over here, we have all the targets of that relation. and the sort of place where they lived. Here's some terminology to sort of ground that, right? The set where you begin is called the domain. These are going to be the inputs that you use. And remember, you have to use every input in the domain. So if a rule actually doesn't work for some element, you have to exclude that from your domain. Then we've got the range. These are the outputs that get used. 4 and 5 were the only outputs that got used. There's a special name for the place where the outputs live called the codomain. We won't focus on that so much in this class. We'll focus mostly on domain and range. So what relations do is they formalize and they give like a rule and a symbol structure for the idea of input and output. But you're allowed to take an input, like 1, and send it to multiple outputs, like 4 and 5. So a function then is a relation where each individual input is sent to exactly one output. It's not sent to multiple places. It's not sent, to some places sometimes and other places other times. It's sent to exactly one output. So here, the problem was that there was repetition in the first position, the input position. We could also see that in the mapping diagram because there are 2 arrows coming out of a single source. So let's fix this previous example. Let's change the relation by omitting one of those arrows. Let's say the arrow from 1 to 5 to make this into a function. So now our relation looks like this. It sends 1 to 4, and also 2 to 4, and 3 to 5. Notice there is no problem with repetition in the second slot, in the output slot. That is fine. That's still a function. What that looks like in terms of maps is that your arrows could go both into some number. That's fine. But every single source only has 1 arrow coming out of it. Now, there's other good ways to represent functions, and 2 of those are tables and graphs. So here I have the relation. We'll talk more about this parentheses notation in a moment. I have this relation put over here where we sent 1 to 4 and also 1 to 5 and 2 to 4 and 3 to 5. Here the problem was repetition of the inputs. That makes it not a function. Over here I've given our function a name, f, and I've said that f sends x to 4, 2 to 4, and 3 to 5. Repetition of the outputs is not a problem. This is still a function. Notice what that looks like with a graph. Now, for very simple relations like this, where we're just talking about sets of single points mapping to other sets of single points, it's sometimes nice just to plot them as dots on a graph. Here I've taken the input set, 1, 2, and 3, and the output set, 4, 5, and 6, and I've sort of put them on number lines represented by the x and y axis here. So here I have 2 dots above the x equal 1 position, right? I have one at y is 4 and another at y is 5. It's this vertical stacking that's going on here that makes this not a function. Over here, we omitted that 1 point, and now we have sort of, well, we had it over here too, but now we have this horizontal sort of repetition. That's not a problem. That will still be a function. So this would be the graph of a relation, but not a function. This is a graph of a function, and all functions are also relations. We will come back to this in later videos to talk about the vertical line test. But for now, let's talk about the most common notation for functions, f of x notation. This is going to put a name for a function out front, oftentimes f. Then inside parentheses, we put its input, and that's x. And then over here, where I have my ellipsis, there will be some instructions or rules, right? Something that tells you what to do with this input of x. You should think of the f as being the name of the function. Just like variables get a letter, functions get a letter too. It's not a variable. It is not a variable. It is a machine that eats variables. It takes in variables and then it spits out something else, a dependent variable that's based on the rules or whatever the function's instructions are. Now, when we write this whole collection of symbols, pronounced f of x, then altogether, you could think of that like the total output. You could think about this expression, f of x, as meaning y. That's totally fine. If you want to think about f of x and y as being very, very similar to each other, then go right ahead. Usually, I mean, you'll even often see it where the y-axis is called the f of x axis. I prefer to call it the y-axis, and then I'm very specific to call my function f, or sometimes f of x. But this all together, you should interpret this as the output symbol or collection of symbols, and you should associate that with a dependent variable. Now, very specifically, even though it's a parenthesis next to another letter, it's definitely not multiplying. This is why I wanted to stress that f is not a variable, it's a function, right? That is notation abuse, a more use of parentheses in a weird way. That's, yeah, totally. That's legit. And a lot of people think that this says f times x. It very much doesn't. It very much does not. That's not how you should interpret those symbols. The way you should interpret those symbols is f of x. And even though of, in other cases, I mean, this is even linguistical notation abuse, right? Because of often means multiply. No, 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 no. This means input. This means input. This means x is going into this machine called f, and f is going to do some stuff to it. And then your output is going to be this whole collection of symbols, f of x. The thing in the parentheses is to mark what you plug into f. So I want you to take these down as critical notes. Write this down so I know you watched the video. Show it to me later. What is this function notation? F of x notation. Let's call it that, right? Number one, there's a name. Number two, there's an input. It's inside the parentheses. Number three, there's rules. I'll give you an example in just a second. And this whole collection out here, you should think of as the output. What happens when you plug in x into those rules? You get something. We'll call it f of x. So here's an example, right? What happens if I plug in x into f? I get x squared plus 1. So this is often the way we write the rules. There's a generic stand-in variable, x, and over here I say what I do to x. I square it and I add 1. And that whole thing is summarized as the output f of x. What if I plug in 2? Well, then you're going to do 2 squared plus 1. That's 5. So we would say f of 2 is equal to 5. Then what if I plug in this weird triangle? It does not matter. Just square the triangle, right? Whatever goes in here, even if you don't necessarily know what it is, no big deal. Just do whatever you would have normally done to x to that new thing. And in particular, sometimes we'll plug in expressions of x. I want you to just do exactly what you would have normally done to x, but now you need to do it to the whole thing. So in this case, I plug in x plus 1. So what I'm going to do is I'm going to square it, and I'm going to add 1. That's it. That's function notation. Okay, let's do some practice exercises. This is your praxis for the day. Which of these following are functions? A, B, C, or D? Just decide whether or not you would call that a function or not. And number 2, I want you to, as we say, evaluate the function. What do you get when you change the input from x to the following in A, B, C, and D? Pause the video at this time, and we'll see how you did. All right, let's see how it went. So, first of all, we scan through our parentheses here, and I notice there is repetition in the first slot. So is this a function? No, it's not. What about this one? Okay, we've got an arrow coming out of the A, out of the B, out of the C. So it is a relation. It does assign a value to everything in the domain, and it only assigns one value to everything in the domain. So this is definitely a function. Here in my table, in my input column, I have a 1, I have a 2, I have a 3, I have another 3. Well, there's 2 3s here. One gets sent to 3 and the other gets sent to 4. That's assigning 2 different values to the same input of 3. So no, this is not a function. About this one, is there any vertical stacking? No, there's not, right? For each one of these, if I look at the x sort of vertical line, x equals whatever this number is, x equals 1, x equals 0, x equals minus 1, right? There's only one value that gets assigned to each one. So for example, here, 1 is sent to 1, and 0 is sent to 0, and minus 1 is sent to 1 again. There's no problem with repeating horizontally. It's repeating vertically we're checking for, and there's none of that here. So this is a function. All right, now let's evaluate this. Evaluating this means replacing x in these rules with these inputs. So for example, this one here is 3 times 2 plus 1, that's 7. This one here is going to be 3 times, now it's 2x in the input slot, so we put 2x in for our x instead, and that's just 6x plus 1. There's no way to evaluate this any further. We don't know what x is. And what about x plus 2? Okay, so this is going to be equal to 3 times x plus 2 plus 1. Okay, distribute your 3. That's 3x plus 6. Add another 1 to that. That's 3x plus 7. Alrighty, that's it for this video. Thank you for your patience and have a great day. Good luck with your studies, and I'll see you in the next